we do in the last two lectures is to survey relatively briefly a bunch of different useful constructions you can do within the setting of Operads. So I think I'll start with discussing envelopes of the Operads. So when we write Sm from infinity for symmetric monoidal in this strong symmetric monoidal functors. Then from the way we've set up our definitions, Sm hat is merely a subcategory in Operads. It's the subcategory where the objects are equally approached with our Cartesian vibrations, and the morphisms are those that preserve all Cartesian morphisms. And so the idea of this envelope construction is that this functor has a left adjoint. And the symmetric monoidal envelope and not only does it sort of formally exist, but we can give a very concrete description of what this envelope looks like. So we try and briefly go through that construction. Yes, one thing we can show, if I have some infinitely calibrated factorization system, C is the LTR, and I should say when I write CLTR, what I mean is that this is the subcategory of C with the morphisms coming from the two classes in the factorization system. Then I can look at the infinity category of arrows in that right class. So that's a full subcategory of the arrow category of C. And what I want to say is that if I look at the evaluation in one functor, which is a functor that takes every arrow to its target, this is a Cartesian convolution. Right, the Cartesian morphisms, those that squares. So this is also the target. Then the morphism is something like this, with the square, and this Cartesian is the top map lies in the left class. So the idea is that if I have an object, and I have a morphism down in C from its target, then I can factor this composition using the factorization system, and that produces a unique morphism of this shape. So you can think of this as giving us a functor from C with infinity categories, taking object X to CR over X. So the target, the value in an object only sees maps in the right class, but then we have a functoriality for all the morphisms using the factorizations like this. You can use these things to build up kind of free vibration constructions. In particular, well, we can also show if I have the P from A to C, such that E has P coefficient lifts of the left class in C, then we construct then there's a free way. There's a way to freely adjoin Cartesian lifts of all morphisms in C using this construction here. This arrows from the right class. Namely, if I take the final product of E with this R and boundary, so the final product is by evaluation at 0, and then I have a function to C that uses for evaluation 1. We can show that this is the Cartesian evaluation where the morphisms look like right. So I have an object here, so that's some like E and E, and then I have a map in C from PE to X, and then I'm supposed to be able to transfer that along a map from X to Y. And so I first do the Cartesian thing from this arrow thing where I factor this, so it's not to line R. So I factor the composite as something in L and something in R. And then I use that in E, I have Cartesian lifts of things in L. So this map is called, say, F, that's the map that lies in L. And then I have a Cartesian morphism over F in E. Say E bar, let's say F bar. And then you can prove that this actually gives you a Cartesian vibration on this spiral product. And moreover, this has a universal property. This is free in the sense that I have a Cartesian vibration F to C. Then I have given on my functor E to C, and some map over C. And I assume that F preserves the Cartesian lifts of CL. So those are the ones that I assume existed for P. Then given this, there exists a unique extension to its final product. Say prime such that if prime preserves all Cartesian morphisms. The idea is that if I start with F, I can build this F prime by saying that if I have some object here, that's some pair consisting of X and the map Px to C, which is in the right class. Well, in curly F, I can I have a F of X, that's some object, but then I also have a Cartesian lift of my, I put everything F, maybe I can illustrate this to G. So I have this G, and in curly F, I have a Cartesian lift of F of X over G. So I can send this pair to this object in F. And this turns out to be the unique way to extend my functor f to a functor f prime that preserves all co-Cartesian morphisms. Okay, so that's a pretty general construction you can do. And so in this operad context, remember we start with an infinity operad that in particular has co-Cartesian lifts of inerts, which are the left class in a factorization system on a pointed set. And so if you buy this theorem, then I can universally add co-Cartesian lifts of actomorphisms to get a co-Cartesian vibration, which is the symbol of O, defined to be O plus over finite pointed sets with the active error category of this. This has a to be the left adjoint this fusion of symmetric monoidal Operads, provided that this envelope actually is symmetric monoidal. And well, it is. If you look at what's going on, if I take the fiber of n O n, then that's going to give me O plus over F star with active arrows in F star over n. And so I want to decompose that into, well, I should say, first of all, if I take the fiber of 1, then if I take n equals 1 here, then because every map in finite pointed set, every object in finite pointed sets has a unique active map to 1, this F star act over 1 is just the active category. And so I just get the active subcategory of O, that's the subcategory maps over actives in star. So I want to prove that this guy is equivalent to the product of n copies of O act. And that basically is because for the video Operads, I have an active map. So an object here is explicitly an object of n O n is x in O, and then follow that down to F star for P, then I have an active map from P of x to n. And so then the point is that this allows me to break x into a list of n things. So this, say if this was some n in this active map, tells me how to decompose m as a sum of n things, and I can use like inert lifts in O to decompose x as a lift of as a list of n things in O. So it's fine. So yeah, so I'm using well. Right. Well, yeah, I'm not sure what to say about this, but I have them the inert map. I have the inert maps for I that I keep going on about. And so if I now factor this composite as something inert and something active, then using the co-Cartesian lift of this map, I get some co-Cartesian map from x to xi, and I. And then the point is that this construction, sending x to the list of these xi's, provides the equivalence I'm supposed to have over here. So this is symmetric monoidal. It's equivalence. Okay, so I've formally said that there exists the symmetrical envelope. So let me try and say a little more completely what this looks like. So we have N over star. This is symmetric monoidal, and its underlying category is the fibrate 1, which I said was the active category of O. So symmetric monoidal structure 1. All right. So I can think of objects as lists. So starting in O1, and then morphisms, and then lists of multi-morphisms from out. Because the multi-morphisms are supposed to be exactly the things living over active maps we want. And this has a symmetric monoidal structure, which you can think of as just being given by concatenating lists. So, for example, if you look at the envelope of the terminal object, the commutative operator, which is those finite sets mapping to itself by the identity, what you get is a F star act you can identify just with a category of finite sets. So we have a monoidal structure, symmetric monoidal structure on finite sets given by concatenation, and this is just a just a union of finite sets. Okay, so we have this junction. Okay. Now, as this example shows, this left junction does not preserve the terminal object. So I can modify this picture slightly and instead think of the envelope as giving me a functor into symmetric monoidal categories over the envelope of the terminal object, so over finite sets with the operadic monoidal structure. And then I get that this has a right adjoint as well. I just have to modify it a little bit, namely this U will be given by taking symmetric monoidal category, C tensor over F product. Well, for my junction, I have a unit map from finite pointing sets into F product. That's just the unit as a like the 1-point set as a commutative algebra in F. And then I can take the pullback of these. And that is what I'm U of C tensor. So I get this new junction. And then now I can show if I take this U and combine it with the N, I get the identity. Because what does this mean? It means that I take operad. Or if I'm going to do that, then I take its envelope. Just this pullback. By definition, this is the pullback of O over with the second R category. And then I take, to define U of that, I take another pullback back to F star, but then this composite is just the identity. And so what U n of O ends up being is a pullback over the identity, and so this is an equivalence. And well, this is actually the co-unit of the adjunction. And so the fact that this is the identity tells me that if I think of the envelope as a functor into symmetric monoidal categories over F coproduct, then N is fully fixed. Actually, I can think of operads as some. So this gives me a way of thinking about infinity operads as certain symmetric monoidal infinity categories with a symmetric monoidal functor to finite sets. And you can actually characterize the image quite concretely. And this is an observation due to Charlotte Lacan and Jan Schreinerwoman. That if I can identifies infinity with full subcategory of symmetric monoidal indicators over a fill product, satisfying the following condition. Well, on those C tensor over F product equifiber, which means, so in general, it means that if I have phi from n to n active, I can look at the fiber of C tensor at n, go to the fiber at n by using co-Cartesian lifts of phi. I'll get a commutative square over the same thing with F. And the condition of that is that this is a pullback. And you can actually reduce this to just the case of phi being the active map from 2 to 1. And so this is the same as saying that if I look at the tensor product functor from C cross C to C, and I use my functor to finite sets, and this is pullback. So a little more explicitly, this is saying that if I have an object in C over a coproduct of finite sets, so if X maps to any coproduct M, then I have to be able to write X as X1 tensor X2 with, maybe I'll pull it, yeah, okay, with X1 over M, X2 over M in a unique way. And the same with morphisms in C, they also have to decompose over products. So this kind of condition has been studied quite a lot in the category theory literature. It's almost called like the hereditary condition. So, and it appears, for example, in connection with these Feynman categories of Kaufman and Ward, which is actually just a characterization of things that arise as envelopes of colored operads in the one category setting.
Does one also need to require for the Lurie?
Jan is shaking his head, so I guess not.
Like I don't need that over the unit first.
Well, it must follow from this condition that is true over the unit. Yeah.
Somehow, I don't remember.
Nine.
I'm also going to discuss the other composition, symmetric monoidal to Operads. I'm very happy you discussed this one. But I would also like to discuss that.
Well, I mean, so if you have one of these C's over a finite set, you're sort of supposed to look at just take the sub-operad of things that live over the 1-point set. That's not a symmetric monoidal category. It's not close to the tensor product, but it's an operad. And the solution is telling that generates the whole C. So okay, we'll try about that. So if I have this C over F, symmetric monoidal functor, and I apply U to it, what I get is the sub-operad of C on my objects, my over the one element set. So I construct an operad where multimorphism is like my colors of the operad are the things in C and
You forget everything that it's
just C1, and then a multimorphism from like X1 X to Y is a morphism of like tensor product Y over like this. Or a unique map like this, I guess. In C. And so then the idea is that this condition on the tensor product, these decompositions coming from the pullback, tell me that this information generates the whole symmetric monoidal C. Okay. I want to mention also a variant of this, which is the Latin case of Morita. So we can think about this is closely related to a description of classical operas and symmetric monoidal categories called props. So in this infinity setting, I can define a prop is a symmetric monoidal infinity category such that the underlying symmetric monoidal infinity groupoid is free. So I can define, the infinity category of props in this sense as a pullback of symmetric monoidal infinity categories. I can take, if I have a symmetric monoidal infinity category, I can take its underlying infinity groupoid and get a good algebra in spaces. And then there's a free algebra functor from spaces. So I just take this pullback. So saying an object prop is a symmetric monoidal infinity category in the space, such that the underlying symmetric monoidal infinity groupoid of my category is the free thing on that space. See, let's this and then coordinates of tensor product is so free. With the large one next. And so if you look at this envelope, it's the underlying infinity groupoid of an envelope is always of this form. So envelopes are always props. So we get the envelope functor. We can make the envelope functor into a functor from infinity operads with prop. And this is also fully faithful. And we can just try this image. Right, so we can also think about infinity operads as certain props in this sense. I should say this is a little different from the way props are normally thought about in one categories, because people will often say that a prop is a symmetric monoidal category, such that its underlying commutative monoid sets is free. That condition is not invariant under equivalence. So this definition is more like saying the underlying symmetric monoidal groupoid is free, which is invariant under equivalences. So. And I also wanted to mention that, I stated this result that we can characterize infinity operads as a full subcategory of symmetric monoidal categories over F coproduct. But Jan and Charles actually do something much more surprising, which is they can show that we can actually, that's it. So Boardman and Steiner will have also shown that just the plain envelope functor from infinity operads and tap is a subcategory inclusion. So you can actually view infinity operads as a subcategory of symmetric monoidal infinity categories, but yeah, that's a much less obvious result.
It's worth pointing out that the variant was proven before composition. Right. Is the subcategory full or is it any subcategory?
It's definitely not full, but it is but you can characterize so it consists of some objects and some morphisms in symmetric monoidal categories. And somehow if this functor to finite sets exists, then it's unique. And for map to be compatible with it is a property. Okay, that was all I wanted to say about envelopes.
The prop you get in the envelope, what is the space free on? Like the sort of
It's free on the space of colors of the envelope, right? Okay, so that's all I wanted to say about envelopes, and then the second topic I want to discuss is decomposition. Okay, so let me start by recalling what this is doing in the classical setting of one categories. We'll say that C is a small symmetric monoid category. And D is a complete symmetric monoid category where the tensor product preserves these colors in each variable. Then you can now, in the category of functors from C to D, with a symmetric nodal structure. Where the tensor product of two functors is given by starting with I have my two functors f and g, so I can look at f times g from c cross c to d cross d. So I can compose to the tensor product in d. And then over here I have the tensor product in c. And then the fact that d had all these coordinates tells me that I can take the left time extension of this composite along the tensor product. And that's what gives me my tensor product of the functors. So we can write this out using the formula for time extensions as f tensor g evaluated at non c is the colimit over a category whose objects are consist of pairs x, y in C with or not x tensor y in C, and then at that object I take f of x tensor of y.
GeoTop.
Nice. So this method of the structure has the property that commutative algebra objects in from CD with this tensor product are lax symmetric monoidal factors. From C to D. So basically, I have a natural constant, the commutative algebra here is given by, well, I have a natural transformation from I have some functor f, and then I have to have a multiplication, which is a transformation from f tensor f to f. And given such a natural transformation amounts to giving for the economic C and C, I have a map from this colimit to f of c. And then we're using the property of colimits. This is saying I should have a compatible choice of maps for every map x tensor y. I'm giving C and C and x tensor y. Nothing to C. Compatible maps and x tensor of y. F of C. So this data is kind of generated by taking the ones you get from this map is the identity. And so this is by the compatibility condition. So this has to specify this data is enough to specify maps f of x tensor f of y, f of x tensor y. So that's the lax symmetric model structure on our front one. Right, in this characterization, you can generalize to a universal property of this state convolution structure. But then you can also generalize the whole thing to the infinity upright setting. So next time we state this universal the existence of universal property in that setting. we have the following. First proof on small class and more generality by Lurie and the final version of higher algebra. So let's say that C is a small symmetric monad within the category. And O is the infinity operad. When there exists a day convolution infinity operad, and I call day of C O. So with the universal property that if I take algebras in this thing for some infinity operad P, this is naturally equivalent to taking algebras for P possibly epsilon with C tensor in O. So this is like the Cartesian product in operads of P and C tensor. And if my operad O is a symmetric monodal infinity category in tensor with as before, D co-complete and the tensor of preserving preserves coordinates variable, then they seem to the tensor is actually the symmetric monodal. With the tensor product given by the same formulas in the classical case. So I'm saying that if you can generalize the day convolution to a target that's just an operad, doesn't have to be symmetric monoidal, but then you just get the day convolution operad. But the source, well, in the statement here, the source has to be symmetric monoidal. This certainly does not exist if I take C tensor, replace C tensor by some arbitrary operad. So in particular, from this universal property, you can extract that the underlying infinity category, so the phi 1 of base CO is functors from C to O1. Right. And this universal property, so I'm saying what I have here is P times C. So and this is an equivalence of infinity categories, but like if you restrict to infinity groupoids, what this is saying is that they O is an external hom for the Cartesian product. Note that this does not always exist. Infinity is not Cartesian closed, not in complete generality. But you can extend the construction a bit to the case where C is something called symmetric monoidal. So I guess various people prove a version of this. I think I should go to Barwick. The last one is Shaw. The construction was corrected in the later paper of Shaw, and then it's also it's in Kinnich's paper on Rich infinity operads. Right. Okay. So this thing exists. I want to discuss a variation of it that's also important. Which is if I consider the pre-sheaf functor from small infinity categories to co-complete infinity categories, you can show that taking pre-sheaves with its covariant functionality, so we get a functor from infinity categories to complete large infinity categories. This is lax symmetric monoidal. With respect to the Cartesian product of infinity categories and this co-complete tensor product over here that I introduced at the very end of yesterday's lecture. So this the tensor product so that co-limit preserved functors out of C tensor D are the same as functors out of C cross D that preserve co-limits in each variable. So, in particular, if C is a symmetric monoidal infinity category, this implies three sheaves on C gets a symmetric monoidal. Well, it's a commutative algebra in co-complete infinity categories, and so it's in particular symmetric monoidal with tensor preserving co-limits in each variable. And then you can get this construction kind of independently, but Bossman shows that this agrees deconvolution from C and spaces for the Cartesian product. In the case of deconvolutional pre-sheaves, this gives an alternative way of constructing it. And this also gives you, the main theorem, we had a universal property for mapping into the deconvolution, but for pre-sheaves, we also have a universal property for mapping out. So this is the non-universal property. Make that co-limit preserving symmetric monoidal functors from pre-sheaves on C D are the same thing as just plain symmetric monoidal functors C D. In other words, you get a symmetric monoidal upgrade of the universal property of pre-sheaves as the free co-completion on C.
How is that a variable?
So yeah, really variant is not the right label. But what I'm saying is that there are two ways of constructing a symmetric monoidal structure on pre-sheaves on C. If C is symmetric monoidal, one is to use this general deconvolution theorem.
Which is how? Yeah, I'm also missing a little bit of an example of.
Yeah, so I'm going to discuss some examples of deconvolution next, but yeah, so the idea is that if I start with C, I get a deconvolution. Well, I get a symmetric monoidal structure also on C op. So I take deconvolution for C op and spaces. That'll give me a symmetric monoidal structure on pre-sheaves. But then also, because you can prove using that for this co-complete tensor product that pre-sheaves is lax symmetric monoidal, we have to show that we get that pre-sheaves on C is a as a commutative algebra object in everything they had CC. And so what I'm saying here is that these one can show that these two are actually equivalent. And then from the second description, you get this universal property for mapping out of the convolution on free sheets. Okay, so I don't have much time left. I started about half an hour late, right?
Just 5 minutes. And then you have 10.
Sorry?
You have 10 minutes.
Okay. Yeah, so then in the last approximately 10 minutes, I want to discuss some examples. Right, okay, so here's one simple example. Let's consider this the arrow bracket 1, so the category 0 to 1.
Sorry, one question. This pre-sheet buffer, is it for symmetric monoidal or is it really just lux?
It's just lux. Wait, no, I guess it is symmetric monoidal, yeah. Previous on C cross D is the tensor product, yeah. Okay. Okay, so if I take the arrow, this has a symmetric monoidal structure where the tensor product of I and j is the minimum of I and j. So it's 0 unless I take unless I and j are both 1. And so then if I have C some symmetric monoidal infinity category compatible with coproducts at least. I get a deconvolution on the arrow category of C. So what the formula for the tensor through arrows gives you, if I take x to y, tensor with x prime to y prime, I get the push-out product of those two arrows. So I get x tensor y prime, push out under x tensor x prime, and tensor. I probably don't mean co-product, so I probably should say push out. So, and then that push out maps to y tensor y prime. So this is the so this push out product tensor on arrows is an example of a deconvolution. And so if you apply this to a Cartesian monoidal structure, so if I put C cross, you can show that this, well, under reasonable assumptions, this localizes to give a symmetric monoidal structure on C star, so C under the terminal object, pointed objects in C. And you can regard this as a full subcategory of the arrow category, since there are no non-trivial endomorphisms of the point. So this and under reasonable assumption in C, this has a left adjoint. The left adjoint L from the arrow category of C to C star, which takes an arrow like monoidal base point in y mod x, which is to say y controlling the external point. Yeah. And so, well, yeah, I'm not going to state the general theorem since I have only 10 minutes left. But like there's a general theorem about how when you can localize, if I have a localization of a symmetric monoidal category and the localization is compatible with the tensor product, then you can use the tensor product on the subcategory where, like, if I have C0 of E and the C0 is a full subcategory of C, and there's a left adjoint L, and well, I want to say that if L the map is an equivalence, then so the local equivalences are closed on a tensor under something. I'm writing the general theorem now. If this condition holds, then C0 is symmetric monoidal with tensor product given by L of my tensor in a big category, and then I localize down to C0. Okay, so in this case, what I'm trying to say here is that this push-out product deconvolution localizes to give me the smashed product on some tensors in C star. Then another kind of example, if I look at commutative monoids in some infinity category, the finite products. So that's a full subcategory of functors and finite pointed sets in C, satisfying this Segal condition that we've seen before. Then if C is is nice, then this right hand side will have a deconvolution from the smash product of finite pointed sets and whatever, and the Cartesian product in C. And we can show that this localizes, we give a tensor product on commutative monoids in C, and also to commutative groups in C. So this was first, I mean, not in this way, but this tensor product was first constructed by Boardman-Vogt. And the circulation that we get is from a deconvolution is due to Rune and Schlang. So we have the tensor product on like commutative group objects coming from the deconvolution, and this you can really think of as an infinity version of the tensor product of linear groups. Okay, and then finally, we mentioned one way to set up the smash product of spectra. So you can view spectrum as a functor from finite pointed spaces to spaces that is reduced, meaning that the value of the point and it should be excisive, meaning that if I obtain f on a push-out square, I get a pullback. That's a special case of this excisive condition. You get that the value of f at the n sphere has to be the loops on f of the n plus 1 sphere. So looking at the spheres, you get a spectrum in the expected sense, and then that actually determines the whole functor. But if you view it in this way, there's a nice way to construct the smash product using deconvolution. So spectra, functors from finite pointed spaces has deconvolution from smash product in finite quantum spaces and the Cartesian product in S. And this localizes two spectra to give the smash product. And this is actually, you could view this as an infinity version of like classical constructions in the model category world of smash products and diagram spectra. So in particular, a model like this is actually considered in paper and diagram spectra by Mundell, May, Jed, and Shipley. So if we can construct the smash product spectra in a way that is quite classical in this sense, using their convolution. Okay, now I will start.
Questions for Rune?
So, whether you talk about big patterns or more general operating, do you know what kind of, do you have any examples where you take the envelope and you round in switch of one of the big categories where you get like a plus, right? Like, so if I took the cyclic opera and my this envelope is a classical kind of prop plus some type of symmetric or regenerate value. Do you know how to see any of that type of duality stuff?
I guess Jan should be answering this question. You can use cyclic operads as some kind of symmetric monoidal vector structure.
It's easier to say for modular. So there, if you take the envelope and you get a prop, then it's you can characterize them among symmetric monoidal infinity characters. Yeah, and one of the axioms will be that every object is dualizable.
Yes, it would be hard. You need non-degenerate strict grammar. I don't fit very well.
There are other questions? I guess you get a break before you have to suffer through another hour.